over there. Don't forget that you have some videos that are coming up due. And we have a test next week. I expect the test to cover chapters 1 and chapter 2. I'm going to go through kind of an overview of chapter view, and then we're going to do each major food molecule, carbohydrates, proteins, and lipids in a little bit more detail. So that'll be today and Thursday that we'll be doing that. So I'll assign a second homework assignment that will be due next Monday that will cover some of the stuff in chapter 2. It'll be due Monday at midnight. So any questions there? All right. Thursday. I believe it's this Thursday. That's what I have in my mind. Let's say it's Thursday. Okay, and then there is the study 1 analysis that you are supposed to turn in today. If you turned it in online, that's fine. Does anybody have it on paper that they couldn't do it online? Okay, great, because I prefer it online. Thank you. All right. Let's see. So I don't normally put together a study guide, but the reason I put the objectives on the overviews for each chapter is that's kind of your study guide. Those are the things I'll be asking. The other thing I do is I provide you with old exams. So if you look in the files at the old exams, you should see how I've asked questions before. So major food molecules, we're into chapter 2 here. So what I'm going to try to do with this presentation, as I said, is give an overview. So the first thing that we're going to talk about is polarity, because the polarity of different kinds of food molecules is really going to affect how they behave both in the foods and in your body. And so that's really kind of the key component for understanding food. And so that's going to be based on electronegativity. And so we're going to look at how we can figure out which elements are more or less electronegative. And then we also, aside from the major food molecules, are going to have some minerals, and those are mostly going to be ions. And the way we determine what kind of ions we have is where it is on the periodic table. So we saw the first column is a +1, the second column is a +2, and then over on the other side, the noble gases are 0, and then the next column is a -1. But we can more broadly divide metals from non-metals. We talked about this briefly when we talked about the periodic table, but we'll go over that again. So those points are going to come pretty quickly, and then we're going to look at 4 major food molecules. One of them is water. Water doesn't give you any calories, but it is very important in food. And then the other 3 provide most of the calories that are in food. Now, if you do biology, they would throw in another set of molecules that are biologically important, and that would be the stuff that makes up like DNA and RNA and those kinds of things. We're not going to deal with that so much because they're not calorically important. All right, so polarity, what is it? Polarity is caused by the electrons not being spread out evenly. So when we have a neutral atom, we have all the positive charge in the middle, and then the electrons are on the outside, and they balance each other out. But if I have the electrons kind of gathered to one side, then that side of the atom, or if it's a molecule, that side of the molecule is going to be a little bit more negative. So if you imagine trying to hold a flat plate that has something round on it, like in the book I use the example of grapes, it would be really hard to get those to spread out very evenly. As you kind of tip the plate, they would kind of roll to one side. And so that kind of happens in polar atoms or polar molecules and things like that. So our favorite example of a polar molecule, 2 things that can cause a polar molecule. There's actually a little bit more details in this, so anybody who's had Chemistry 111 will know that we go into a little bit more detail in this. But if it's not a symmetric shape, or if I have elements of different electronegativity. And so that's where we're going to have to talk about electronegativity. So our classic example is water. So water has two different elements, oxygen and hydrogen. And the oxygen has a much stronger preference for the electrons. We call it electronegative. It draws on those electrons. And then the hydrogens have less. So we either say it's less electronegative or sometimes we'll say it's electropositive. So it also has this bent shape. So it's kind of symmetric, but it would be more symmetric if they were going straight out from one another instead of the hydrogens pointing down. So that little bit of a decrease in symmetry means that we can kind of push all of the electrons that are trying to get to the oxygen upwards and have the more positive side downwards. So in chemistry, we have a couple of different ways we might illustrate this, and you'll see these symbols. I'm not going to have you draw them, but you'll see them from time to time. So one of them is this little squiggly here. That squiggly is the Greek letter delta, and it's the lowercase. So if you've seen the big triangle, that's also a delta. This is capital D in Greek. This is a lowercase d. And you put a positive if that side is a little bit positive. So the whole thing isn't a +1, but it's a little bit more positive than the other side of the molecule. And then where the oxygen is, we've got more electrons hanging out there. That's going to be a little bit more negative. So we say it's partially positive or partially negative. And so at the top here where the oxygen is, this has that symbol with the negative. That's partially negative. Where the oxygens are, you'll see the little squiggly with the positive. So that's partially positive. And then next to the bonds, you see these arrows, and this is a special kind of an arrow. The arrow points in the direction of the electrons, and it's got a little cross at the end. So I find that little cross very helpful because it looks like a plus sign. So the end that's not where the arrowhead is the positive side, and then the arrow points towards the negative side. And so this just kind of tells us which direction it's polar in. And so if I'm just looking at these two atoms, the bond is polar in this direction, and this bond is polar in this direction. So in some ways, they're sort of balancing each other out. They're kind of both pointed towards the middle, but they're also both pointed up. So if we kind of combine those together, and mathematically you do that with vectors. If you remember in algebra class somewhere talking about vectors, that's how you do this. We're not going to worry about the vectors. You could combine those two, and overall it's just straight up and down. So we say the whole molecule is polar like this. Each of the bonds is polar like those. We're more concerned about the whole molecule than each of the bonds. All right, so important thing to remember about water is that it is a polar molecule that is very polar, and that polarity causes it to be attracted to other polar molecules, especially water. And so we could end up having water that is so strongly attracted to each other that it stays in the liquid state more than other molecules of its size. So if we look at water, I'm just going to throw out some numbers for you. You don't need to memorize these just yet or ever. Water has a mass of 18. Methane has a mass of 16, and ammonia has a mass of 17. So those are very, very similar in weights, 16, 17, 18, very close to each other. But both methane and ammonia are gases at room temperature. Not only is water a liquid at room temperature, all the molecules are stuck together, but as I raise the temperature, I have to go all the way up to 100 degrees Celsius in order for it to not be a liquid anymore. So those water molecules really want to be next to each other. So that's one property of water that's really important. And then another thing is, because it is strongly attracted to other molecules, it dissolves things really well. Particularly, we'll see sugar and some ions. So it's good at dissolving, and it has what we call a high heat capacity. We'll come back to those topics in a minute. Okay, so we use very different words to talk about the adjective something is polar is the adjective, or the noun, a polar object isn't called a poloid or something, it's called a dipole. I don't know why we have these very different words, but if you hear the word dipole, it just means the thing is polar, okay? So a molecule with polarity is called a dipole. Water is a dipole. And two dipoles can be attracted to each other, two water molecules or water and sugar, by what are called dipole-dipole forces. So we're going to talk about several different forces throughout the semester that cause molecules to be attracted to one another, and this is one of the stronger ones, dipole-dipole forces. Now in chapter 2, there is a box. If you click on the side for the box, it talks about hydrogen bonding, which is kind of supercharged polarity. And we'll talk about that a bit. For right now, I just want to focus on the idea of, is it polar or is it not polar? Okay, so water attracted to itself by dipole-dipole forces. Questions so far on polarity? Yes. Okay, so I said water is really good at dissolving things, but it doesn't dissolve oil. We know that oil and water don't mix. So if we're trying to figure out what it will dissolve, we say like dissolves like, which means if it's polar, water will dissolve it. If it is not polar, it will not dissolve it, okay? So if we want to say, let's see, we're looking at honey, and I'm going to tell you honey is polar. It's got sugar in it. I told you sugars were polar. Is it likely to dissolve in water or in oil? So those are our choices. It has to dissolve in water or oil, or you could say both, or you could say neither. All right, but I stop the thing now. All right, so water is the correct answer on this one. We had a range of answers here, but most people got water. Most people who had the whiteboards also said water, so that's good. Okay, so how do we know honey is going to dissolve in water? Because both of them are polar. Like dissolves like. Okay, so now we are going to, oh, and I should say, for the purposes of knowing when they're going to dissolve, ions, which are fully charged, are going to act more like polar molecules than not polar. So ions dissolve well in water, like salt dissolves in water, but salt does not dissolve well in oil. Okay, so the next question is similar. You're going to do the same kind of thing. Oh, I thought I had two questions. Yeah. Okay, well, we're skipping the next one. All right, electronegativity. The tendency of an element to attract electrons in a bond. So we said this is what's determining where the electrons are going to go. So when I say oxygen is more electronegative, we're saying oxygen has a tendency to attract the electrons in the bond. So the bond is made up of two electrons, and so the two atoms are playing tug of war with it. And the one that is more electronegative is stronger at pulling those electrons towards itself. So electronegativity is on a scale from 0 to 4. This scale was developed by Linus Pauling. He's kind of a big wig in bonding chemistry. We actually have this picture out on the wall here. He's the third one over. And he's kind of an interesting guy. He has 2 Nobel Prizes. Now, there are a handful of people who have 2 Nobel Prizes, most of them in the same area. I think Niels Bohr has 2 in physics. You've all heard of Madame Curie. She's one of the few people that have a Nobel Prize in 2 different areas, one in chemistry, one in physics. So she did a lot of work with radiation about electricity. So Pauling has 2 Nobel Prizes. One of them's in chemistry for this bonding work, and the other one is a Nobel Peace Prize. So talk about different areas. So he was a pacifist, and during the the Vietnam War, when a lot of Americans were kind of opposed to us being involved in that. He was somebody who was really anti-war at that time and ended up getting the Nobel Peace Prize. He also had this thing about vitamin C. So when we talk about vitamins, we'll get back to him. He was really a super fan of vitamin C. He would have been one of those people that was like trying to promote his superfood on the internet these days. And, you know, he would have had his own like marketing company saying, buy my vitamin C pills with 3,000 milligrams, 10,000 times your daily dosage, or whatever. He loved vitamin C. So we'll get back to him. Anyway, so scale of 0 to 4, very small range there. Okay, so fluorine is the highest. So fluorine is a 4.0. And that's important to remember because everything gradually falls away on the periodic table from fluorine. So as you go from right to left away from fluorine, fluorine is a 4, oxygen 3.5, nitrogen 3, carbon 2.5, boron 2, beryllium 1.5, lithium 1. So the farther you get away from fluorine, the smaller it is. So rather than always having to look up the numbers, we're just going to say, well, how close is this element to fluorine? Now it does the same thing going down, but the difference between the first row and the second row is pretty big. So we went from 4 to 3.5 going to the side. Fluorine is 4, chlorine is 3.0. So we have a big drop, almost a whole unit's drop going to that second row, and then the others is a smaller drop. But if I were to compare, say, boron and oxygen, oxygen's right next to fluorine, boron's farther away, so oxygen is more electronegative. Okay? So that's kind of how we do it. So while officially we go down to 0, I think the lowest element that has been measured is cesium, and that's at like, I think it's like 0.2. We don't technically go down to 0, but we're not going to deal with those elements anyway, so we're just going to work. All right, so I am going to, throughout the semester, call hydrogen our problem child. It is out of place in a lot of ways. It doesn't behave exactly like things in its group, but it doesn't behave exactly like things elsewhere. So in its column, you see everything else is red and it is green. So it is green because it is a non-metal, where everything else is a metal. But it does form a +1 charge like the others do. Okay. One of the ways that it's out of place is on the periodic table, it's really far from fluorine, right? So you think its electronegativity would be somewhere close to lithium, but it's not. It's actually somewhere between boron and carbon. So it's not all the way over to the right, not all the way over to the left, it's just misbehaving, okay? So we're going to say that it's very close to carbon. And if you ever have to ask, is hydrogen more or less electronegative than something, just assume that it's the same as carbon and then ask yourself what carbon. All right, so this is a periodic table that gives actual numbers. So we see fluorine is 4.0 here, carbon 2.5, and the hydrogen, it's actually 2.1. So I said it was between boron and carbon. So it fits in between those. Carbon is something that is in practically every food molecule except for water. So you know, that's why I compare it to carbon, because boron doesn't show up a lot in food, so we won't talk about boron very much. And then as we get farther away from it, we're going to have the numbers drop off. Now, one of the ways that we can distinguish elements from one another is by whether they are metals or non-metals. And so generally we say that if that electronegativity is less than 2, we're going to call it a metal. And so you can see there's a line here, boron, silicon, germanium. These are 2, 1.8, so it's really close to 2. Arsenic is 2.0. These are all like right at 2. And then the stuff over here is less than 2. And so most of the periodic table is made up of metals. And you'll see on this chart here, those same elements are in brown. I don't know why they have arsenic in green instead of pink there, but in most places it's in there. So those are our semi-metals that we mentioned last week. And they're just kind of borderline. Sometimes they act like metals, sometimes they act like non-metals. Arsenic is being one of them. Do you think that shows up in food a whole lot? No. So we're not going to deal with the semi-metals very much. But the metals have things like Fe. Anybody know what that is? Iron. So that's important in our bodies and in food. Sodium and potassium help run our cells. Calcium is important for our bones. So metals are important in food, even though they're not part of those larger molecules. Okay, so, and we'll call those minerals. There are some minerals that come from negative ions. Phosphorus is really important, and sulfur is important, so we'll see those show up as well. Okay, so you may or may not be able to see how close they are to one another, or you may or may not be able to see the numbers. But if you had to compare phosphorus, the letter P, so it's right there, to chlorine, which would you say is more electronegative? Shout it out. Phosphorus or chlorine? Chlorine is going to be more electronegative because it's closer to fluorine. Okay, and then if we check the numbers, chlorine is 3.0, phosphorus is 2.1, 3.0 is bigger, so yes, it is more electronegative. Okay, so I think we have another question. And now if we compare carbon and oxygen, and we're going to use those a lot, so you need to be able to find that on the periodic table pretty quickly, that second row with nothing on top of it. Which one is more electronegative? And if you, everybody said oxygen. You guys are awesome. Okay. Try not to make these questions too challenging. Okay, this one is a little bit more challenging though, okay? Nitrogen and hydrogen. So remember, we're gonna, instead of looking at where hydrogen is, we're gonna look at where carbon is. So which one's more electronegative, the nitrogen or carbon, which is similar in electronegativity to hydrogen? Okay. Oh, I need to start the question, sorry. Doesn't seem like it's too challenging. I'll give you a question like this on your homework that will be due next Monday. And you'll be able to, there's a table in the book that you can look at if you want to refer to the numbers. On the test, you'll just need to know which one's closer to 4. All right, so I'm going to close this. Anybody object? Responses, everybody said nitrogen, y'all are awesome. I said we were going to talk about ions, and these are important because they can be in minerals. So metals, all of the stuff in the middle, all of the stuff on the left-hand side, and some of the stuff down here, like lead is a metal, obviously, all of that, they will only form positive charges. Okay, so we call those cations. That was a term from last week. Generally, their electronegativity is less than 2. Then our nonmetals typically have an electronegativity that is 2.5 or higher. And so those are the ones that are in green up here. They are going to form anions or negatively charged particles. So we saw that this whole column here with fluorine, those have formed a -1. Oxygen and sulfur like to form a -2. So what about the elements in between, our brown elements here? Sometimes they act like metals, sometimes they act like nonmetals. So almost all of them will sometimes form a positive charge and sometimes form a negative charge. But even when they're forming those charges, they're only sort of acting like ions. Again, we're not too concerned about them, but if you're wondering about that polarity. Now, I will point out, and back up to the questions, but on the periodic table with the numbers for the electronegativity, the elements that are right in here actually had electronegativities above 2. They were more like in the semi-metal range. Anybody know what AU or AG are? Gold and silver. And so this column, copper, silver, and gold, that's called the coinage metals, because we, in ancient times, made coins out of those things. Now we use nickel and zinc and some other stuff. The reason they used these is that these were not reactive. They wouldn't start to rust the way iron would. They wouldn't dissolve, things like that. They were also precious metals, but they're not reactive. And so that's true of this column, and it's also true of these right here. So anybody ever heard of platinum? Platinum's a pretty precious metal. It's actually more precious than gold is, more expensive than gold is, and also not very reactive. Palladium, very similar. These are used in cars, in the catalytic converters. And then iridium is more rare, rhodium is more rare, but they're also ones that are not very reactive. So that's just kind of a side note that we do have some exceptions to this electronegativity rule. They're not important exceptions to us, but if you notice that, that's my comment.
A lot of times people steal your catalytic converter from under your car because of the metal value.
Yeah, have you ever heard of that being a thing, that you could get your catalytic converter in your car stolen?
Something on campus.
Has it really? I've heard that, I drive a Prius, and I've heard that that's one that's particularly susceptible to that, so I get a little bit worried about that. But yeah, so they will go and they will take apart the catalytic converter and sell the metals to somebody, and the amount of money that they get for the very small amount of the metal, precious metal that is in there, is nowhere near the cost of replacing the catalytic converter tube. So that frustrates me to no end, that they're not even getting the benefit that it's costing me when they do the crime. So, yep, that's definitely a thing. All right. So, when we have dipoles, we said they are attracted by dipole-dipole forces. When we have cations and anions, we say they're attracted by ion-ion forces. So there's some logic there. And then I also said that water can dissolve salt. Water can dissolve ions. So we would call that interaction an ion-dipole interaction. Okay, so there's some logic here on how we name these forces. Okay, so we talked about where elements are on the periodic table and whether they would be metals or nonmetals, and we said the metals are going to be positive, the nonmetals are going to be negative. So magnesium, Mg, in this column, is that going to be a cation or an anion? All right, so most people said cation, have one person said positive. So when you do your homework, if I ask you to type something in, I probably would have said the correct answer is cation, but I would also call positive correct because that's what cation is. And so I go through when there are questions like this, and if somebody said positive instead of the thing I thought you were going to say, or let's say you put cation, but you spelled it wrong, you put 2 T's or something, and it says, nope, that's wrong, I will give you credit for those things. Okay, so cation is correct. What about oxygen? And everybody go. All right. So we talked about oxygen, or sorry, we talked about water as one of our major food molecules. That one has no calories. There are 3 kinds of food molecules that do have calories, and they fall under the category of organic food molecules. So we'll talk a lot about organic chemicals in this class. Organic in chemistry means something very different than it means out in the real world. So out in the real world, you might think of organic as meaning natural, or you might think of organic as meaning not man-made, or you might think of it meaning we didn't use chemicals in making this. So my first objection to that is everything is made of chemicals. Water is a chemical. Air is several different chemicals. So you can't make something without chemicals. But in organic chemistry, we are talking about things that have a lot of carbon. They're carbon-based. Generally, they will both have carbon and oxygen, or carbon and hydrogen, but there are a few exceptions. Always carbon. So these molecules tend to be bigger. So our water molecule just had 3 atoms in it. Our food molecules that have carbon in them tend to be anywhere from 20 atoms to 20,000 atoms. Okay, so much bigger molecules. So we are going to start by talking about the smaller ones, and then on Thursday we'll talk about the larger ones.
So are we doing a test on Thursday or are we doing it
Next
Thursday? Got it.
should be, I think, the 16th, if I remember my dates correct. Okay, so I'm going to briefly describe this. If you want to look at it a little bit further, in Interchapter 1, it kind of describes in more detail how you get from showing all of the atoms to showing these line structures. But because there are so many atoms, you know, if you have 20,000 atoms, you obviously don't want to draw them all. And even 20 atoms is a lot to draw. We leave out the hydrogens and the carbons. So what we do is we draw lines, and the lines are showing connections between carbon atoms. So I would draw, say, this. That has a connection between a carbon here, 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 and here. So there are 4 carbons on it, okay? So every corner is a carbon, and every end that doesn't have a letter on it is also a carbon. And then carbon likes to bond to 4 things. So the way we know where there are hydrogens is for every carbon, anything that's not bonded to another atom is bonded to a hydrogen until it gets to 4. So this one right here is bonded to 2 carbons here and here. So it's also bonded to 2 hydrogens. This carbon here is bonded to this carbon, but nothing else. So that means that it needs 3 extra bonds, so it has 3 hydrogens. So that's kind of the logic that is used. Mostly what I want you to recognize is that when we are looking at these symbols, they will almost always have lines in them. And where you see those corners, those are carbon atoms, and that's why it's a molecule. Lines aren't representing something other than atoms. It's just simplifying so we don't have so many C's and H's on the page. If it's an element other than carbon or hydrogen, it is always shown. So usually that's going to be oxygen. Sometimes we'll see nitrogen and a little bit sulfur and phosphorus, but usually it will be oxygen. Now, if there's a hydrogen that's attached to the oxygen instead of the carbon, we'll usually write that one, because then we're not, counting up how many bonds carbon has. So, let's see. Okay, so let's take a look. And then whenever there is something other than carbon or hydrogen, so if there's an oxygen, if there's a nitrogen, we call those functional groups. And so throughout the semester, we're going to talk about several of them. We're going to introduce the most important one that shows up all over the place today. Okay, so 3 major food molecules. The first set is carbohydrates. So carbohydrates means carbon, carbo, plus water. So that's why we have plus water. Okay, so all of the formulas have some number of carbons, and then it always has water in a 2-to-1 ratio, or hydrogen and oxygen in a 2-to-1 ratio, the same ratio as in water. So for sugars, they come in simple and more complex varieties. And so the very simplest sugars are called monomers. And we're going to build those. There's going to be building blocks for a chain called a polymer. Okay. So simple sugars have different names depending on how they're connected together. Most of them have actually the same number of carbons, hydrogens, and oxygen. Most of them are C6H12O6. So you possibly had a biology class in high school where you learned about glucose with C6H12O6. So that's, this molecule is glucose. This one is galactose. This one is fructose. And then this one is deoxyribose. So deoxyribose is the D part of DNA. So DNA actually has sugar in it. Okay, so you'll notice that in some cases, the carbons are shown, but usually we just leave them out. Okay, so when we see lots of lines, that's how we know there's carbons in there, even though we're not going to see the letter C a whole bunch. What else do you notice about these simple sugars? What are some commonalities? Yeah, the names all end in "ose," and so that can be a way to help you recognize when something is a sugar or a carbohydrate, is that "ose" ending. Now, not every sugar will end in "ose," but if you see "ose" in a chemistry word, it's probably either a sugar or a carbohydrate. Okay. What about the structures themselves? Did you notice they're all in a ring? So this is a 5-ring, 5-ring, a 6-ring, and a 6-ring. Okay, so sugars tend to form these rings when they're in chains. Now, when they're by themselves, they can unfold. But when we look at them, just for the sake of helping to remember which ones are sugars versus other things, we're going to try and draw them in rings. Okay, so sugars tend to form these rings, and then the rings will attach to each other to make bigger molecules. All right, so we can build the sugars that we are more familiar with by putting together combinations of these. The most important one is the one listed first here, glucose. So glucose is in every important carbohydrate. Sometimes it is the only thing in the carbohydrate. All right, so a disaccharide, so saccharide is another way of saying a sugar. A disaccharide has 2 of these to put together. So if I put together glucose and galactose, I have lactose. Anybody ever heard of lactose before? So I personally am lactose intolerant, which is a shame because I love dairy. So lactose is found in what? Milk, yeah. And so our bodies don't naturally break down this into the 2 simple sugars, but it produces a chemical called an enzyme that will break it apart, and then our body can break it down further. But for people who are lactose intolerant, either your body doesn't make very much of it, which is my case, I make a little bit of it, or it doesn't make it at all. And so it just passes through your system. So you might be thinking, well, that's great because then you can eat sugar in the milk form and no calories. Except for that our guts are all lined with bacteria, and bacteria are really good at breaking these down. But instead of breaking them down into the two sugars, it breaks it down into gaseous molecules. So people who are lactose intolerant, if they don't also take lactate or some other lactase supplement, tend to be very gassy. Okay, and then this molecule is probably the sugar you're most familiar with. This is table sugar. Table sugar is glucose, which is the six-membered ring, and fructose, which is the five-membered ring. Anybody ever heard of fructose before? Some people know, some people yes. So fructose is kind of easy to remember because it comes from fruit. So the fruit can tell you that where it comes from. And it's very common in honey, has a lot of fructose in it. You may have also heard of high fructose corn syrup, and when we get to our chapter on sugar, we'll talk about why that's not as big, bad, and scary as people make it out to be. Okay, so disaccharides are combining these two things. Notice glucose is in both of those, right? We could also put together two glucose molecules, and we would call that maltose. All right, now if we put together more than just two of them, we call it an oligosaccharide. So oligo means some, not many, more than one, more than two. Or we can do a polysaccharide, and that would be many. Those would be long chains. So an oligosaccharide might be a short chain that has just a handful of these. And then the polysaccharides are going to be these other things. So I don't have names for any oligosaccharides. As we make longer chains, the molecules get less sweet. So the chaining of things together kind of changes the shape in such a way that our taste buds can't taste the sweet as much. So we're going to talk about, when we get to the carbohydrates, these different categories: the amylose, amylopectin, and glycogen. Those are all things we can digest, which means we can get calories from them, and they are all starches. So when we say a potato has a lot of starch in it, or we say a banana has a lot of starch in it, it's got a lot of amylose in it. Glycogen is also starch, but it is found in animals. So starch is found in your hamburger. There's glycogen in your hamburger. There's just a lot of protein, so you don't notice the starch. Cellulose and pectin make up cell walls in plants. And cellulose in particular is when we can't digest. Our body doesn't break it down. And that acts more like you would think it would. Since we don't break it down, it just kind of passes through our body and, you know, no calories for us. But it does more than that. It also absorbs extra liquid. So if you've got a lot of fluid in your digestive tract, it'll kind of sponge that up. But it also breaks up the solids to keep them from packing together too much. So basically it's fiber, and it keeps you regular. It keeps you from having too runny or too hard stuff. Does anybody need this slide anymore? I know okay, so that's overview of carbohydrates. We'll talk in a little bit more detail later. Lipids are what we call fats and oils. And there are kind of four areas that we will focus on. So triglycerides are normally what we think of as fats and oils. When you get coconut oil or vegetable oil, or you see fat on a piece of ham or a piece of beef, that's what that is triglycerides. There are also cholesterol. I know you've heard of cholesterol that gets measured in blood tests and things like that. And it's a completely different shaped molecule, but just like fats and oils, it's non-polar. Okay, so I guess I should have put it on the previous one. Carbohydrates, those are all polar. lipids here are non-polar. Okay. Now the fats and oils have pieces to them, and one of those pieces is called a fatty acid. So we'll talk about that and how that's different from the bigger molecule, the triglyceride. And then there are phospholipids. We're not going to talk about phospholipids too much right now. Hopefully we'll be able to get to phospholipids at the end of the semester, and they're really interesting and can do a lot of really cool things both in food and in your body. So these are kind of